Hello everyone, this is Gabita Ramesh, Assistant Professor EC Department from Saint Martin Engineering College. So today we discuss a topic called CMOS fabrication, stick and layout design. And before that we'll see how a CMOS device can be fabricated. Let us go through the video, how it will be done the fabrication and what are the different steps involved in this fabrication. So let us see the video of CMOS fabrication where the N well as well as a P well are diffused on a P substrate. And let us go for that. I am taking a single wafer on which a P substrate is diffused, and on the P substrate over the surface of this we implant a silicon dioxide layer by using the process called oxidation. And after this a photoresist material is added on the surface of silicon dioxide layer for uniform distribution of the silicon dioxide layer. And to diffuse the N well on the other side of the P substrate, we go for photolithography where we use N plus well. That mask is used to diffuse, as I am showing here, diffuse one side of that N well that you are showing there. So this is your N well mask, and where this mask is used to what? Remove the photoresistant material as well as the silicon dioxide layer, and after which we add hydrofluoric acid to form that, to remove the silicon dioxide layer. Then by using a diffusion process we diffuse N plus region on the other side of the P substrate. Let us see here, as you are seeing here now. So this is what we are adding a photoresistor strip off by using that photoresistive method that we are removed. And here we are using the process called diffusion. In the diffusion process we implant that N well on the one side of the P substrate. Now the N well is diffused on the other side. Now in a single substrate we have both N well as well as P well. As we know that CMOS consists of both NMOS as well as PMOS transistor. So in this a single substrate I need to implement or fabricate PMOS as well as NMOS transistors. For that purpose, as we know that PMOS transistor that will consist of the terminals called source, drain and gate, as well as N well will consist of source, drain and gate, and over which first we need to form a polysilicon which is diffused on the surface of this P substrate, and in which by using that we will form a gate layer which is showing here with the red color, and then after we use two N plus dopants to be diffused by using N diffusion process, as well as P plus dopants are diffused on the N well, and N plus dopants are diffused with the P substrate to form the source and a drain that terminals. Now let us see. Now the oxide pattern and N plus regions is formed here. Now to be formed, for that purpose I am using mask again, that N plus diffusion. That N plus diffusion are depleted to the N well as well as to the P substrate. Now this will act as a P well, and where N plus regions are diffused, and as we know that N well other side, that N well itself, what we need to diffuse the P plus as well as the N plus regions to form that the substrate also. Though in this CMOS we have substrate that is shorted with the what source. Now we using that P plus diffusion, and the P plus dopants are diffused into the P substrate as well as the N well. Now this will form this is N well, where P plus regions represents the source and drain, and where the N plus is the substrate. In case of P substrate, we are N plus regions are source and drain, where the red color which shows is a gate terminal, and a P plus diffusion is there. Now after forming this, we need to remove the thick oxide field again by using process called etching. Then after we go for what? Forming the metal contacts. The metal contacts are again using by mass we can diffuse these metal contacts on the source, drain and the substrate as well as on the N well, as we are seeing here. Now this is the way we need to etch the part of the silicon dioxide layer where I want to diffuse the metallization, that is the metal contacts, and this process is called adding the metal contacts on the source and drain is called metallization. So in this way we will form a CMOS transistor where it will consist of P substrate as well as N, and this will be your PMOS transistor and this is your NMOS transistor. So let us go for So stick diagrams. In this six stick diagrams, so we'll start with the basics like NMOS transistor. So here in NMOS transistor, as we know that source and drain are there along with the gate terminal. Now let us see how they are represented and how what we use to represent this NMOS as well as PMOS, that is N plus diffusion and P plus diffusion. So now coming to the contact cards. Now here see, now encoding for single metal NMOS process. So NMOS process, as we know that one is your thin ox, that is inactive, and the second is so this is your thin ox and this is your polysilicon. This is acts as a gate terminal, and where as we know that NMOS itself is a NMOS transistor. The transistor only will be implemented the NMOS logic, where we have two types of transistors. One is enhancement type, other is depletion type. So hence I shown only the one type, that is N plus active region, where the polysilicon will form the gate terminal, and the metal, the color is what blue color, that is used to represent the metal contacts, and where the two, that is N diffusion or P diffusion polysilicon, if they are made contact with the metal, then we should use to show this contact, that is small circle with the black, and whereas this is your layout encoding. Now this layout encoding is what, where the same thing is represented in a rectangular form with the left hand slant that represent the green color, whereas the polysilicon with the right hand slant, that is with the red color, and whereas the blue metal is the vertical lines, these represents your metal representation. And the overclass used to what form that P plus diffusion. Let us see now how the transistor is formed. Now let us go for N type transistor. Now this is N type enhanced main mode transistor. Okay, now so this is what your NMOS transistor, and NMOS transistor we have so that source and drain and gate are there. Now how to form this transistor? So that red over green or the green over red, whenever these two are overlapped on each other, there is no contact made on this. When these two overlap each other, then the transistor will be formed, and that type of transistor nothing but your N type enhancement transistor. Next is what, this is symbolic representation where we have, and this is a mask layout similar to your stick diagram. Now the red over green or green over red with the slant lines with the rectangular box shown in here, and this type of notation will be used in what layout designs. Next coming to this N type depletion mode transistor. So here N type depletion mode transistor, it is like NMOS transistor only but depletion type. Here what I used, a yellow square box where that green crosses the red or red crosses the green, and that an implant is drawn, that is with the yellow color a square box is drawn, that represents your depletion type transistor as we are representing. Okay, and the same type of that box, that is yellow color box, that is overlap over, that is represented on the overlap of what green all over the polysilicon. Now this is what P type enhancement type and CMOS well process in this. So this is your PMOS transistor, the PMOS transistor. Now that with the bubble indicates your PMOS transistor, that gate and source and a drain, and here demarcation line is especially used, and it is similar to that, but except that here I am using yellow for the P diffusion, whereas in NMOS transistor we use green color, and that for N diffusion. Now here the red, that is poly over yellow, that is red over yellow or poly over the P diffusion will form a P type transistor that we are seeing, and the demarcation line which is used to distinguish between what, this NMOS transistor and PMOS transistor. Now let us go for, so let us take one example like called NMOS transistor, PMOS transistor, is CMOS transistor, where we have both NMOS as well as a PMOS. So here I use one trans, that is what I said, like, so on the power supply where we are connecting the power supply, this is CMOS inverter that I am drawing here, where to the power supply we are connecting, this is your CMOS inverter, and to which we need to draw stick diagram. As I represented just now, that PMOS transistor will be represented like, that is, this is a ground terminal where a common input is given as input to both PMOS. This is PMOS transistor and this is NMOS transistor, both are, to which we apply input, and the combination where we these two transistors are connected, here we take output. Okay, let us go for the simple operation of this. In simple operation, what I can see that when my input is logic 1, so that makes the transistor NMOS on, and this transistor on, and where is the PMOS transistor on, off. So whenever this happens, thus that PMOS transistor which acts as a open circuit, and this is disconnected from the, that output terminal disconnected to the VDD, where it is connected to what? A ground. That means when my input is logic 1 and the output is connected to the ground, that is nothing but 0, that is 0 volts. It can be treated as what? Logic 0. And similarly, whenever my input, that is logic 0, when my input is logic 0. Now when my input logic 0, what? That makes your transistor NMOS is off, and then the PMOS, that is output terminal which is connected to the VDD through the PMOS. And in this case, the output is approximately equal to VDD, and this is considered as logic 1. So this is a way of operation. Let us go for the drawing the stick diagram over by using word CMOS transistor or CMOS inverter only. This is your CMOS inverter. Let us go for drawing the stick diagrams. So stick diagram, for that purpose, as we know that blue color is used for metal, where the cross mark indicates the ground as well as the VDD. Now we'll see that how to draw it. I'm taking a blue color which is used to make the connections VDD as well as supply. So I'm using blue color. Now the first, the power lines are drawn with blue color, where this is what, so I'm drawing the blue color. So this is your VDD, that is power supply, and this is a ground, or also called VSS. Now a cross mark is made on VDD as well as ground, indicate that these are the power and ground rails which are connecting the PMOS transistor as well as NMOS transistor. Here we can dictate, like the PMOS can be formed by what? A red over yellow, that forms your PMOS transistor, or yellow over a red. So I'm taking a color red, that represents your, let us take yellow, that represents your P diffusion. I'm taking a yellow line over the which I need to draw a red color. That red color is, when I draw this, that will form your NMOS transistor, that is PMOS transistor, and the PMOS transistor is formed by whenever that red crosses your yellow, that is a diffusion. I'm not okay. So let us see this, and that red over okay, right. Okay, we can go for what? I need to draw a red color, that is your that represents your poly, and I use the yellow color where this forms your transistor. I think what? Red over yellow or yellow over this red, that will form a PMOS transistor. Similarly, that NMOS transistor can be formed by using what? A red over N diffusion, that is a green color. So I'm using green color here, that green color, and over which I need to draw the polysilicon, and this polysilicon will form a PMOS or NMOS transistor, and NMOS transistor itself. Okay, so Okay, ready.
అక్కడ ఇచ్చారు చూడండి, అక్కడ మీ చేయి బొమ్మ ఒకటి అక్కడ ఉంది చూడండి, అవి కలర్ మోడ్స్. ఇప్పుడు అండ్ బ్యాక్ సైడ్, దాని కింద బ్యాక్ సైడ్ రాస్తే ఎల్లో వస్తుంది.
Okay, done. Right, so we go for eraser to rub this. Right now we go for NMOS transistor formation. This can be done by drawing a red over a green. So no. So I am using what, a green, and on which I'll use a red color to form your transistor. Now this is your PMOS transistor and this is your NMOS transistor. So like we did here, now this is what, this is your PMOS transistor that I have drawn here, and similarly this is your NMOS transistor that is drawn here. Now I need to make connections, that input is connected to this PMOS as well as NMOS, and the output taken where the PMOS and NMOS are joined together. Now these two joinings are done by a metal that is used blue color. Now I'm using a blue color here that is used to join these points, and this point towards the supply and this points towards the ground. And here that polysilicon itself can be used as a make connection as a input. So let us say these two are combined together to form NMOS transistor. So there is a CMOS transistor. Now the combination of these two where we apply input, and across from this metal we can use a polysilicon as well as the metal blue color which is used to take the output. Now this is the way we need to draw the stick diagram. Let us go for simple view of the layout of your CMOS in layout design. In this we go for, what, the drawing the layout design. So in this PPT, and we'll see now this is your NMOS depletion load inverter. Now as I said that, so in this case we use, this is a depletion type transistor, and this is what your this is depletion type transistor. This is your depletion type in NMOS, depletion type, and this is your enhancement type. Okay, so both are NMOS only, but one is depletion type, other is enhancement type. Now here the gate is shorted with the source, where to make the transistor, the depletion mode NMOS transistor always conducts. So instead of that, so let us see now this here. Now this implant, whatever I'm showing here, that implant will represent, see, green over red over green, or that green over red, that will form a transistor, that is NMOS transistor itself. When I draw the implant here, that implant will show that this is a depletion type, and where there is no implant, that represents your enhancement type. Now this is one of the type of your NMOS inverter. Now let us go for, now this is what CMOS inverter. Just now we have drawn. There are other way of drawing the diagram is different. We can draw it any manner. Now here we have that NMOS transistor as well as a PMOS transistor as I'm representing here. Now this is your NMOS transistor, this is PMOS transistor, and this is your NMOS transistor. This is in CMOS. See, as I said, red over green and red over yellow, that will form a transistor. Now this is one transistor and this is one transistor. This is a formation of transistor, this is a formation of transistor. This is PMOS and this is NMOS. So this is how we represent, right? Next we go for a layout. So layout nothing but simply we have the rules like lambda based design rules that we have in CMOS design, that is lambda based design rules, we call it as lambda based design rules. Again further they are classified into 1.2 micrometer lambda based designs rules, or 2 micrometer rules are there. Okay, so let us go for representing your the layout design of your in CMOS transistor. In this Now this is an example for 2 input CMOS NAND gate, and before that we go for this is an OR gate, and this is one of the example of this. Let us go for this. Now 2 input NMOS NAND gate, or else we go for CMOS NOR gate. Now this is mask layout. This is called transmission gate symbol, where we have both NMOS transistor and a PMOS transistor. Now this is your PMOS and this is NMOS. So transmission gate nothing but which simply transfers the data from the input to the output. So this is used to transfer the level of voltage, where let us say my input voltage is 5 volts. I want to transfer the same 5 volts to the output side, and where these the threshold voltages of this PMOS transistor VTH, we call it as VTH of the PMOS transistor, VTH of the NMOS transistor will affect the output of this transmission load. Now it will not be exactly equal to 5 volts, it will be a little bit down. And now this is how we drawn the layout diagram of this. The layout diagram is similar, like the black color represents your contacts, and here where we have this. Now red over your yellow and the red over the green, this will form your NMOS transistor, and this will form your PMOS transistor. And where we apply here the input and where we take the output from this. As I said that the blue colors are used to apply the input, like to make the contacts between the diffusion layers, that is P diffusion as well as N diffusion layers. Now this is one of the example of this stick diagram as well as the layout. And let us go for one more example. This is what your functional, let us take a function called f is equal a dot b plus c. So this is called a function, a logic function a dot b plus c. Let me explain this. Now a dot b nothing but you are performing the AND operation, where the plus is nothing but your OR operation. So AND means you need to what? Right, let us see here. Now where AND is performed, these to be what? When AND function is performed in logic, then these to be what? In parallel. And where OR gate, OR function is performed, they are in what? Series. Now as you see that a dot b, these two appears in parallel, and whereas plus c, and this plus c is what? Added in series with that, and this is added to the supply, and is a complement that represents output is inverter, that we use CMOS technology to implement this function. And coming to the downside, because this can be represented in different manner, like you may have some doubt, like so how this is drawn. We have, so like I said, a pull up network as well as pull down network. Any CMOS logic that will consist of a pull up network, that is PU, and this pull down network, where the pull down network, the pull down network is connected to ground, and pull up network is connected to what? The supply VDD. Now this is your ground terminal, and to which we apply some input here and here. Now this is called your pull up network. This is your called pull up network, and this is your called pull down network. So how to draw this? So pull down network. Now the exact opposite of this pull up network can be drawn here in the pull down mode, where see here the C is connected what? In series with the parallel combination A and B. So now the C is connected in parallel with the series combination of this A and B. As you see here, now here these two are in parallel, whereas these two are connected in series. But to the parallel combination of AB, the C is connected in series, and where here to the series combination of AB, the C is connected. So in this way we draw the pull up and pull down network in case of any CMOS logic. Now we can draw that stick diagram. This is your stick diagram only. In the stick diagram, as we know that first we need to draw the power supplies and a ground, as we have here the power, and this is your ground, this is your VDD, and this is your VSS. And see, I want two transistors, Either you can draw like this or like this, and this combination can be applied to VDD, or the C itself can be down and connected towards this pull down network. Now here shown that, so this is your transistor A and this is your transistor B, which are connected in parallel as we seen here, where the red over this diffusion, red over this diffusion, that is yellow diffusion, forms transistors. These two are what? Yellow, red over yellow means PMOS. This is PMOS transistor and this is your PMOS transistor. And one more, we have PMOS transistor, that is what? A C transistor, red over again diffusion. And these two are the parallel combination of A and B are connected to what? C. Now here the C is connected over which the red is drawn, and this forms your transistor C. And similarly, now this is the connection that we used here. The brown, dark brown can be used, or the blue can be used as a metal. Now coming to the down part, that is pull down network. Now how it can be drawn? Here these ABC in pull up network are PMOS transistors, and ABC in pull down network are NMOS transistors. So that means the pull down network consists of NMOS transistor, pull up network consists of PMOS transistors. And how to draw the NMOS transistor? Red over green. And see here, this is one more where this red is formed, the red over green, this forms one transistor as you are seeing here. Let us say this is C as per the figure, and where AB are connected in series, and this is what? A red over yellow or green, red over green, this is forms transistor A. And here this can be sometimes dark brown can be also used, okay, and this forms transistor B. And to the series combination of this, C is connected in parallel. Now whenever that diffusion layer which makes contact with the metal, we need to draw a black contact that represents your connection is existed like this. The AB series combination is connected with the C in parallel, that is connected to what? Ground. This is connected to ground. Now this is not required, this is just over of this. Next, coming to here in the pull up network, similarly AB are connected to the supply here. So the diagram is somewhat different. Now here AB are connected to supply. See, when the diffusion is make contact with the VDD, we need to make contact, that is with the black color that I am showing here. But there is no contact can be made when A and B transistors connected in series. Why? Because these are transistors, PMOS transistors. So you can use yellow color, that is a P diffusion, a red form, so directly you can make contact, but there is no contact made on this. So next, to join these two, where to join these, the transistor, that is, this is a pull down network with the pull up network. So what I am using here, metal from here to here, a blue color metal or a dark brown can be used. Now this is what we made connection here, and between the pull up network and the pull down network, that is. Now where we apply the input, both at A, B, C, inputs are A, B, C. Now this is what input A, and the same combination can be used. I will show here. See, now A, the same input, whatever we are using, the same input can be here we use. Now A is a common combination we can use. This is a common input, and this is A, and the B, and this is can be reflected back, and this can be what? Your B input, and the C can be combined, the input can be combined, and this is how they made the contacts. Now the red, so A, B are common. Now this is A and B, the common input is A, and B is common. B is common to B and B. These two are shorted with a red color. This is a B input, and the C here directly we are giving. This is a C input. So likewise, we can make contacts. Now this forms your transistor, where we apply the inputs with what? Metal contact. We can use metal contact, or else you can use a polysilicon red as well as a input layer that can be applied to this function. So what do we have? That Boolean function A dot B plus C whole bar. Now this is an example. We have few more examples like this. So where this is only the stick diagrams, and after which use the lambda based design rules, and that are used to form the layout, and from the layout we go for fabrication. Okay, let us go for next. Now this is implementation of that. Now some of the examples are there in well bi-CMOS technology. The bi-CMOS technology nothing but the CMOS followed by the transistor BJT, where the BJT is used. The BJT is used to increase the output level, so that can drive more load or to fasten the device to respond. And here the BJT one transistor, and this is what inverter. Now this is the way we need to draw. So let us go for one more, that is stick diagrams. The stick diagrams are one stick diagrams. So let us go for this and let us see the examples of this. And here we have the basic examples I have shown here. Now this is one more, the basic CMOS AND gate that we already discussed. Now, so this AND gate can be drawn like this is your, as I said, this is a pull-up network and this is your pull-down network. In the pull-down network, we use NMOS transistors. In pull-up network, we use PMOS transistors. As you know that PMOS transistor can be formed by a red over yellow, and the NMOS transistor can be formed by red over green. So this is a way. You can see now where M3, M4, these two are PMOS transistors and these are connected to what? To the power supply VDD. As I am showing here. Now a yellow that is used to represent P diffusion, and over which I am drawing a red, that is polysilicon, that will form PMOS transistor. And similarly the red over green will form a NMOS transistor. And the contact in between the pull-up network and pull-down network can be made with a blue color, or the dark brown color can be used to form that stick diagram of this two input CMOS NAND gate. Now this is how we explained, and we come across what the fabrication steps as well as the stick diagram, a representation of the NMOS as well as a CMOS. That is basic gates we have discussed, inverter and two input AND gate, and followed by a combination circuit that we discussed. Thank you.